Hello, grade 11s. Welcome to today's lesson on the mole. I'd like you guys to start before watching the video by maybe going over to your textbook and reading pages 320 and 321. I want you guys to see if you can figure out what is a mole and why is this measurement used. It'll help you to have some background to understand what I'm going to talk about. Now, a mole is a group. It is like saying a dozen. A dozen is a group of 12. A mole is a group that has a lot more numbers in it. A mole is a grouping that has 6.02 times 10 to the 23 atoms or eggs or donuts or whatever we might be measuring in that grouping. It's a very large number. That number, 6.02 times 10 to the 23, is called Avogadro's number. And Avogadro was a scientist who figured out this nice round number to measure a reasonable amount in chemistry. Anytime we're doing a chemical reaction, we're going to have to ask how much. How much of A do I need to react with B? How much sodium do I need to react with chlorine? How much salt is formed? How would this work? In its most basic level, I know that one atom of sodium reacts with one atom of chlorine to make one salt molecule. I know this will happen. Now, a lot of you will look at this and say, but Ms. Dorm, chlorine is never found as a single atom. It's found as a molecule. It's diatomic. So we can fix this. We could say that two atoms of sodium react with one molecule of chlorine to make two salt molecules. It matters to pay attention whether we're talking with atoms or molecules. This is still a balanced reaction. It would be true, however, if I were to multiply this by 100. I could say 100 atoms of sodium, or 200 atoms of sodium, I should say, react with 100 molecules of chlorine to make 200 salt molecules. But even 100 atoms would be a small amount and too tiny for us to see. What if I times everything by 1,000,000? Would it still be true? Yes, it would. 2,000,000 atoms of sodium react with 1,000,000 molecules of chlorine to make 2,000,000 salt molecules. Well, this is getting to be a better amount, but it's still an incredibly tiny amount in chemistry. So how big of a group do we need for the amount to be reasonable? In reality, we never work with individual atoms or dozens of atoms or hundreds of atoms or even millions. In reality and practically, as chemists, we work with groupings called moles. A mole is a much bigger multiplier. When we multiply to get a dozen, we multiply by 12. If I want millions, I multiply by 1,000,000. When I want to work in chemistry, I multiply by a bigger number and I get moles. The number we're going to multiply by is this big honking number that we have right here. Yes, folks, there are 21 zeros in that number. That number is very difficult to try and type into most calculators. They don't have that many spaces, and so we use scientific notation. To write Avogadro's number in scientific notation, we would write it as 6.02 times 10 to the 23. Now on your calculators, we're not going to write times 10 power of. I know you can make your calculator do that, but trust me, you're going to have nothing but math errors if you try to do that. Your calculator has a button. It's either going to be an EXP button or an EE button. On the Texas Instruments calculators that a bunch of you have, take a look under your second function, comma. There's an EE there as one of your second function buttons. It's in a slightly different place on every calculator, but you need to find it. That button means times 10 to the power of. It means all of those button presses. And it tells the calculator to treat this as one single number. Okay, so if I'm writing Avogadro's number into my calculator, I'm either going to type 6.02x23 or 6.02EE or E23. You'll find some different versions of it on your calculator. But that tells the calculator it is one big number, as opposing to going times 10 power of and hitting all those buttons, which the calculator will interpret as a series of math functions. So you'll get much better results if you learn to use your calculator correctly. Now, going back to our example of sodium and chlorine reacting to make sodium chloride, we have 2 atoms of sodium reacting with 1 molecule of chlorine to make 2 molecules of sodium chloride. These coefficients, the balancing that we've been using to practice balancing equations, can definitely stand for atoms or molecules. But like we've shown, if we multiply that value by Avogadro's number, it could also stand for moles. How many groups are there? 2 groups of sodium atoms, and each group has 602,000 million in them. Reacts with 1 group of chlorine molecules to make 2 groups of sodium chloride. It's just we have a specific group size. The group is 6.02 times 10 to the 23. What I really want you to remember is that the coefficients in balancing can be atoms or molecules, or most importantly and most valuably, moles. I need you to remember that because that definitely is one of the questions that I like to ask on my unit tests and on my final exam. So how do I convert between molecules or atoms, the count that I have, and moles? How do I change it into groupings? It's pretty easy if we think about eggs. If I have 12 eggs, I know I have a dozen. If I have 24 eggs, I have 2 dozen. To change 24 eggs to 2 dozen, you divide it by our multiplier. You divide it by 12. When we're changing between the number of atoms or molecules into moles, again, we're going to use our multiplier, but our multiplier is a much bigger number than it is for a dozen. Here's a great example. Suppose I have 1.02 times 10 to the 26th molecules of water. How many moles do I have? What I'm given is molecules. What I'm asked for is moles. This is a great time for us to use unit factor label method. It's a 4-step method, and we use it over and over and over again to solve chemical equations. Like with any question, start with what you know. Start with the value that they gave you in the question. This question gives us a starting point of 1.02 times 10 to the 26 molecules. So that's going to be my starting point. I'm then going to draw a big long line and cut it off. Now at this point, a lot of people, a lot of different chemists just like to write a times sign. I always like using a vertical line just because my handwriting tends to be messy and it works better for me. If you prefer to write times and to multiply by a series of fractions, feel free to do that. We're changing nothing. It's the same steps. Start with what you know. Now I know I want to get rid of the units molecules. So without putting any numbers beside it, I am going to write the units for molecules on the bottom. I'm going to put the unit I want to solve for on the top. The question asks for moles, so I'm going to put the unit moles on the top. Now this is a truth. What truth do we know? Well, I know that 1 mole is equal to 6.02 times 10 to the 23rd molecules. I have to put something that is equal to each other when we have them top and bottom. We always write the number 1 beside the word mole, and how many particles in a mole? 6.02 times 10 to the 23rd. Now mathematically, when we see numbers on the top of the line, that means we multiply them. When numbers are top and bottom, we divide. So you'll hear me often say multiply across the top, divide across the bottom. If I take 1.02 times 10 to the 26 molecules times by 1, because it's on the top, and then divide by 6.02 times 10 to the 23rd molecules, I'm going to get a value of 169.44. The units molecules on the top are going to cancel the units molecules on the bottom, and the only units that we will have left in this formula are moles. So I'm going to get my answer in moles. This question is self-correcting Because every unit that I wanted to get rid of has been canceled, and the only remaining unit that I want to have is moles, I know I've set the problem up right. I'm going to need you guys to practice using your calculators for these calculations. Make sure that you're using the X or the EE button and not trying to type in times 10 to the power of. You'll find that you might get away with it on very small calculations, but as our calculations progress and get bigger and bigger, if you're trying to not use the functions that the calculator is already built in, you're going to be off by a factor of 10 every time. And if that's what you're noticing, it's probably going to be incorrect calculator usage. I'd like you guys to go, after watching this video, over to Tyler DeWitt's video, and I have the YouTube link here, and I'll post it as well in Teams for you. He's going to explain to you what a mole is and how to do these calculations as well. You need to understand how big of a number it is. A mole is 602,000 million, or 602 hexazillion particles, and it doesn't matter what those particles are. If it was jelly beans, we'd end up with a grouping as large as the planet Earth. If it was if it was donuts, a mole of donuts, we could get back and forth to the moon many, many billion times. A mole is a huge number. The reason we have to use such a huge number is because atoms and molecules are so ridiculously tiny that this is where we get a reasonable amount, an amount that we can actually work with. So after watching my video and popping over to watch Tyler DeWitt's video, what I'm hoping is that you can state for me the number of particles in a mole. Avogadro's number is one that you have to memorize in chemistry and really is one of our fundamental numbers. And then using the factor label method, can you convert from moles to particles and from particles to moles? There's lots of practice for this in our stoichiometry booklet. And you can find the questions that we can work on pages 23 and 24 of your green stoichiometry booklets. I'd like you guys to work on questions 1 through 14 on page 23 and 1 through 8 on page 24 to practice converting between moles and the number of particles.